presentation is all about the periodic table. So we're going to look a little bit about the structure of the periodic table in terms of groups and periods, as well as a little bit of information on Group 1 and Group 7. If you do want more information on Group 1 and Group 7, then have a look at the other video, which has got a lot more detail on those two groups of the periodic table. Bit of a starter though, I want you to have a look at that information there. An element has an atomic number of 19 and a mass number of 39. And I want you to see how many facts you can give about that element, so how much information you can gather from that. So if you pause the video, give yourself a couple of minutes, have a go at that, and then press play when you're ready to go through that. Okay, first thing I'm drawn to is the atomic number of 19. This tells me that it's got 19 positive protons because the atomic number is also known as the proton number. If I know it's got 19 positive protons, I therefore know that it's got 19 negative electrons. And I know that if I take the mass number, so all the particles with mass, 19 of those come from protons, so I subtract the 19 protons from the total mass, and that tells me that there are 20 neutrons. I know from looking at my periodic table that the element with 19 protons is potassium with the symbol K, and looking at the electrons with 19 electrons, I know it can fit 2 in the first shell, 8 in the second and third shells, which leaves 1 for the fourth shell, so its electron configuration is 2881. Now looking at that electron configuration, that also tells me the end number tells me it's in group 1 because it's got 1 in its outer shell, and it has electrons existing in 4 shells, so it's in period 4. There will be more on that in this presentation. So the aim is to understand more about the periodic table. If you can recall the general structure of the periodic table, describe what a group and a period tell us, that's a grade 3. So it's a simple recall, just quoting facts. If you can describe the reactivity of groups 1 and 7, it pushes it to a grade 4. Describing, remember, is just telling the story. What do you know about them? Do they get more reactive, less reactive, and so on? And finally, for the grade 5 plus, you're going to explain how the reactivity changes. So it's building on the second outcome, the description. So not only are you telling me how the reactivity changes, it gets more or less reactive as you go down, you're then going to explain it. So you're going to give some science to firm that up. Why do we need to know it? It's a key document. If we didn't have the periodic table, we wouldn't be able to explain bonding, elements, compounds, protons, neutrons, electrons. A whole raft of information comes from the periodic table. Basically, if you're wanting any sort of career that has any aspect of chemistry, you need to know this document like the back of your hand. Okay. And here it is. Here's the periodic table, building on from Mendeleev's early table, which was put in order of atomic weight. He also left gaps because not all elements have been discovered, and he swapped some pairs around. So if we look at tellurium and iodine here, they don't follow in order of atomic weight because Mendeleev felt that iodine was better suited with all these other elements, all the other enes, if you like, the bromine, chlorine, fluorine. But essentially it's the same sort of thing. This time though, they're put in order of proton number, so hydrogen with 1, helium with 2, and they follow on in order. So the first thing to look at is this here. This is the group numbers along the top, 1 through to 7 and then 0. So group 1, all the elements in group 1, that basically tells us that everything in group 1 has 1 electron in its outside shell. So for example, by the same rule, everything in group 7, they all have 7 electrons in their outer shell. Group 0 is different. You would think that it should be called Group 8, following on, and that would be true were it not for helium. Because neon, argon, krypton and so on, they do have 8 electrons in their outer shell. They have full outer shells. But the problem is helium only has 2 electrons, so it only has 1 shell that can only fit 2 electrons in. So we can't call it Group 8 because of helium, so we call it Group 0 because generally speaking, they can fit 0 electrons in their shell. Their shells are full. Next thing is we look at this dividing line. So as that steps down, everything to the left are metal elements and everything to the right are non-metal elements. So all of these, so about 3/4 metals to 1/4 non-metals. Hydrogen's a bit of an oddity because it's a bit ambiguous because it's got 1 in its outer shell, so it could technically go in group 1, but we know it's a non-metal gaseous element at room temperature and pressure, so it could go over this side. So to save a lot of trouble, we just put it around in the middle, floating. The next thing to draw attention to then, I've just highlighted in a box there hydrogen and helium that runs the full width of the periodic table. This is to show, rather than the rows which are the columns, sorry, which are groups, we're now looking at the rows which are the periods. So hydrogen and helium are together because they're the only elements that have one electron shell. Hydrogen with one in the first shell, helium with two. They are therefore said to be in period one because they only have one electron shell. As we move down, the elements here, lithium for example, it would have two in its first shell, but then that third electron has to go into a second shell. So they're in period two. They have two electron shells. So taking the example here of carbon, it has 6 electrons. So its electron configuration is 2, 4, 2 in the first shell and 4 in the second shell, showing those 6 electrons exist in 2 shells. And that rule follows on as we go down. So the next period down, period 3, if we take the example of sodium, it has 11 electrons, 2 in the first shell, 8 in the second shell, and 1 in the outer shell. And that shows us 2 pieces of information actually. The 1 there shows 1 in its outer shell, and it is indeed in group 1, and electrons existing in 3 shells tells us that it's in period 3. And that rule is the same for all elements. So if we were to look at I don't know, magnesium, we can see magnesium there with its 12 electrons, so it will be 2, 8, 2. The 2 on the end tells us group 2, and the 3 numbers 2, 8 and 2 tell us it's got 3 shells. Just having a look at some of the groups, in particular then group 1. They're known as the alkali metals. They have 1 electron in their outer shell, and they have similar chemical and physical properties. As I say, there's more detail than this in the other group presentation. But just for example, if you add alkali metals to water, they fizz and they move around the surface of the water. They may explode, set on fire, and so on. So that's a common property, which is why they are grouped together. Through that reaction with water, they always form an alkali metal hydroxide and hydrogen gas, which is why we call them the alkali metals, because they have a pH above 7. Okay, so any alkali metal will form an alkali metal hydroxide. So sodium will form sodium hydroxide, lithium, lithium hydroxide, and so on. Hydrogen gas we can test for with a lit splint, and it gives a squeaky pop. And as you move down the group, the alkali metals become more reactive. So lithium is the least reactive, moving down to the slightly more reactive sodium, then more reactive potassium, and all the way to the bottom with francium. Then looking at group 7, they're known as the halogens. Again, they have 7 electrons in their outer shell, so they need an electron to fill that outer shell. Again, like the alkali metals, they have similar chemical and physical properties. Example is they all make good disinfectants. So chlorine is used in bleach, it's used to sterilize swimming pools, and so on. They also react vigorously with alkali metals, forming an alkali metal halide, and alkali metal halides are white solids. And again, conversely to the alkali metals, the halogens become less reactive. So as you move down with the alkali metals, they get more reactive, and the halogens less reactive, which leads us on to a task. What I'd like you to do, I've just told you how the alkali metals get more reactive and the halogens less reactive. I would like you to try and find out why. So whatever electronic device you have, if it's your phone, tablet, laptop, whatever it might be, or if it's just books, have a look through. Let me give you 15 minutes, 5 minutes to find out about group 1, the alkali metals, 5 minutes to find out about the halogens, and then 5 minutes just to jot down a few notes to help you. When you're ready, after pausing it, press play and I'll go through some of the information there. Okay, so if we look first at group 1, as we know, each element has an extra shell as you move down the group. So when you move down, you're moving down to a different period and therefore an extra electron shell. So it means that outside shell is getting further away from the nucleus. Now, if you remember, the electrons are in those shells. And with group 1, they have 1 electron in the outside shell. And the outer electron is being held there by the positive nucleus. As you get further down the group, it moves further away, or it exists further away from the nucleus. The attraction is weaker, so it becomes easier to remove that electron. So the reaction is more vigorous. So if we look at lithium here, the positive nucleus here and the outer electron is quite a small distance. So the attraction is quite weak. So lithium is quite strong, sorry. So lithium is quite unreactive because that electron is held nice and strongly. And as we move down, it's a bit further away, held a bit weaker, weaker still. And when we get to francium, we can see that massive distance there from nucleus to outer electron. It's held much less strongly. So it's a very weak attraction, easier to break off, and therefore more reactive. So essentially the outer electron being further away makes it easier to remove, and therefore it's a more reactive element. If we look at group 7, slightly different. Again, we know that each element has an extra shell, so it's further away from the positive attraction of the nucleus. But with group 7, they're wanting to attract in an extra electron. So whereas alkali metals are wanting to lose that outer electron, halogens are wanting to gain an electron to fill that outer shell. Now, obviously, the closer the element is, so the higher up the group, the closer the outer shell is to the nucleus, the stronger the pull of the positive nucleus, and the easier it is to draw in that extra electron. So the further away, as you go down the group with those extra shells, the harder it is to attract in that extra electron. So they are less reactive. So if we look at chlorine, which is the second element in group 7, we can see that the distance from the positive nucleus to where this electron needs to be pulled in, it's quite close, relatively speaking. Just a disclaimer for all these atomic diagrams, they are only a representation. They're not, accurate sizes, but it's just so you can see what we're talking about. But to pull that extra electron in, it's not a very long distance, so the positive pull is going to pull that extra electron in here quite easy. But if we look at iodine, the distance is much further, which makes it more difficult to pull this extra electron in so that it can fill that outside shell. So essentially, the outer shell being further away means there's less attraction to the nucleus, and therefore it is less reactive. So the reactivity decreases down the group. To finish then, there's a past paper question. It's in 2 parts. So I've put the first parts A and B on this slide, and the rest will follow. So just take 2 minutes, have a look at that and go through it. And then I'll put the answers up and we'll just have a little chat about that. So if you want to pause the video and have a go at those questions, and press play when you're ready for me to go through it. So this is a typical past paper question. It tells you potassium reacts violently with cold water and it forms an alkaline solution of potassium hydroxide and hydrogen. And there we have the word equation. Okay. So what state is it given off? Well, we know that hydrogen is a gas. So there we can see the answer for 1 mark. It is given off as a gas. What type of substance will neutralize potassium hydroxide? Well, as we said earlier in the presentation, potassium hydroxide or alkali metal hydroxides are alkaline, hence the name alkali metals. How do we neutralize an alkali? With an acid. It does say here, ignore any reference to a particular kind of acid. What the examiner is looking for is just that word acid. If you put hydrochloric acid, phosphoric acid, carbonic acid, doesn't matter. As long as you've used the word acid, you will get credit. And finally, what's the pH of the neutral solution? Well, you saw there. Hopefully you know that a neutral solution has a pH of 7. The last part of the question there then. So I'll just give you a few seconds again. So if you want to hit pause and have a look at the question, and then when you're ready, I'll pop the answers up so you can have a look at the answers, and then we will go through it. So there are the questions. So hit pause and just have a go at working through those questions, and when you're ready to press play, I'll pop the answers up. Okay, so again, I'll just give you a few minutes to check that through. So they are the answers to that last slide. So if you need to toggle back on the video just to have a look at your answers, and again, I'll just leave those up